All right, start the recording. Is he giving you the solution?
He's giving me what he thought about it.
Okay.
And then here's the other sequence that I added it to. Dot, dot, dot. Which then it comes out to 0, 1,
0,
0, 1.
0, 1, 0, 1, 0.
That was a lot of work.
That's a monotone sequence. Both of them are.
But this isn't.
Don't you have to do
This
it?
is monotone increasing, this is monotone decreasing, this is not monotone.
What's a simpler way?
Simpler way than that? So what exactly is the problem? You have two monotone sequences,
And their sum is not monotone.
and their sum is not monotone.
Or sorry, their sum is monotone, which is false. Because,
Oh, just because two sequences are monotone, their sum is monotone.
yeah.
That works. I would have used fractions with n, but that works fine.
Okay. And James's problem. What do I do to show?
Okay, so there's 1A. James just did for Jacob, because Jacob didn't know how to do it.
Hey, no, I didn't know how to do problem 3.
B. I thought you would be wrong too.
B is where I couldn't think of a counter yet.
Doing that, I need to upload my screen.
Sophie had me start her class yesterday,
Which class?
Algebra 2.
How was
She assigned me the 3 sections right before quadratic formula.
it? She assigned you what?
The 3 sections right before the quadratic formula. So I didn't get to take them through proof. So I did.
There were no proofs in 3 seconds. Do they use a section?
They're using something weird. I really don't like what they're using. It's so. I could show you the textbook, but it's awful. It's not section, and they're using an online program for the homework. And Sophie's got a teacher edition textbook in the classroom. It's just horrible.
Why is it horrible?
I don't know the word for it. It's like,
Oh, you're saying the
So-
teacher's edition itself is horrible.
it's so like application based.
Yeah.
I
And
figured
so, hey, when students
that you gotta
are
think
having
of
trouble with this,
try
here's
to
this
get
trick
this.
they can use.
Yeah.
Yeah.
Or try to get this, like I
Like it doesn't go in depth explaining why
Well,
things work
you're
and
just
cool
not
things
thinking
about
about
those things.
If
It
one
just
of them,
says,
that's what I don't think.
here's
about.
this formula. If they're not understanding this, try this. If they're not understanding that, try
yes.
this. It's really bad. I don't know why they're not using Saxon.
I didn't particularly like Saxon either.
Well, at least Saxon has a paragraph of explanation before or after some formula. These guys don't. These guys are like, see this problem? Here's the formula.
Yeah, it's going downstream.
James, it might be true.
Old Saxon anyway.
This is where we asked Donnie.
It's hard to think that it's true if they didn't prove it. Think of
What is your question?
My question is,
it. If two monotone sequences are multiplied as monotone.
Two monotonic sequences.
the product of two monotonic sequences is a monotonic sequence.
If we multiply something by a scalar, it just scales it up. It doesn't change its rate at all, right? How do you change a rate?
What are you asking?
By exponents.
are
Rate
two monotonic.
doesn't rate mean the difference between the numbers
Is the product of two
Increase.
monotonic sequences monotonic?
higher per
No.
term you choose?
Why not? Where's the case where it's
Imagine a sequence.
Is this B?
Yeah,
2.3?
yeah.
Let's see what I wrote.
Let me look at it.
1.1 to the n and 1 over n is what I have.
1.1 to the end. See, the hardest part for me was just to find the sequence, to think of the sequence.
So I was just thinking about something that either starts out increasing then decreases, or starts out decreasing then increases.
Time those two together.
I
So
thought-
this is going to start out eventually this is going to grow way faster than this is. So basically I was trying to think about something, so in this case it's going to be something that does something like this.
Right.
Oh.
But I thought the definition of monotone was at a certain point in the graph, if it does that, then it's
No,
monotone.
no, it has to
No.
be consistently.
What were we talking about where it said at a certain point in the graph?
Every monotone sequence.
Oh, we're talking about
version
Subsequence, maybe. Yeah, there's peak indices.
Indices, probably, not.
So when this thing starts, it's more than 1,
We'll see what happens. So
or it's
1,
less than
you
1.
get 1.1. What happens when you plug in 2? 1.1 squared is 1.21 over 2. That got smaller. This to this is smaller, right? But eventually when you plug in massive numbers, this is going to be huge
And that's going to be tiny.
compared to that. Exponentials grow way faster than linears, right? So you can plug into your calculator what you get when you like plug in 100. I'm not sure where it's going to change.
Real quick, if I have a sequence that constantly follows this pattern, then it doesn't have any peak indices because of.
Right.
Okay.
Okay, that's beautiful.
So that's what I have for that.
If the second sequence is the reciprocal of the first sequence up to some point, that's an example. Oh wait, no.
Okay, and we're back. The sequence converges.
It's larger than the reciprocal at one point and then smaller at another.
And one to n does not converge.
That's bounded,
Yep.
and it doesn't converge.
Yep.
All right.
E. Every monotone sequence converges. No. And
There you
doesn't
go.
converge.
All right. And that's 1.2.1, right?
Okay.
All right.
2.
Who's doing 2.2?
Let me.
I'll do
Nope.
A.
Everyone takes a turn. You're doing.
This marker sucks.
I'll do A.
I'll let you run away with that one.
You're doing both of them. You're doing 2.
I didn't even finish 2.
Well, then we're gonna finish it now.
This is true.
That was a long ways walking before you stopped.
Dude, Dawson keeps requesting $1 from me.
Yeah.
Can you block someone on Cash App?
Bet you he does that to every single person on his Cash App. Just request.
Which of the following sequence is monotone? Justify your.
So looking at A and B, which of those is monotone? And what kind of monotone are they?
So A is monotone of increasing.
Correct. Write it out so we can see it. What is A?
Wait, don't we have to prove?
Or sure. You can do that if you want.
Wait, do we have to prove it? Because that's where I got stuck on.
It said justify your answer. Doesn't necessarily mean you need to prove it. Just justify it. Explain why you think that that's the case. If you have the proof for it, great. That's a great justification. N plus plus negative 1 to the n over n is monotonically increasing. Alright, how do you know that?
Because when I plug in, I know that because of this right here.
Okay, we don't need to go through the proof of it. You can't
Well,
do
I
that.
know.
But think about it this way.
That's why I know.
What's the biggest this number can ever be?
Infinity.
No, this
Lower.
term. What's the biggest it can ever be?
1.
What's the smallest it can ever be?
Infinity.
What's the smallest it can ever be?
1 over a very, very large number.
1 plus
What's smaller, negative 2 or negative 1?
1. 1 plus 1.
What's smaller, negative 2 or negative 1?
Negative 2.
Negative 2. What's the smallest that this can be?
Negative infinity.
You can get negative infinity out of that?
Or
Show me how.
negative infinity minus 1.
Just give me a number. Show me how you can get something bigger than negative 2 out of this. What can I plug in for n that gives me something bigger than or smaller than negative 2?
Negative 2. How do you get negative 2 out of that?
Exactly. Can I get something smaller than negative 2 out of that?
Yes.
Okay, show me.
3.
Show me.
Oh, yeah.
Negative 1/3 is smaller than negative 2? Draw a number line. Show me where negative 2 is and where negative 1/3 is.
The heck?
What's the smallest number I can get out of there?
Negative 1.
Negative 1.
Negative 2. Oh, shoot.
Negative 1 is the smallest number I can get out of there.
Yeah.
So this is always positive. The most I'm ever taking away is 1, and I'm always incrementing by at least 1. So this thing can never decrease. Right? Going to the next term, I always increase that by 1, and the most I can ever decrement is 1.
So how would I
So it
say
can either stay the same or increase. You explain just what I said. You don't need to go through writing the proof when it says justified. You can, and that works. I just don't want to take the time to do it right now. Right? So do you understand what I'm saying now?
No, because I can't explain it.
This, what's the smallest this can ever be?
Go 1.
Negative 1. That's the smallest it can be, right?
Yeah.
When we increment this, we always increment it by
1.
1. So the least we can ever increment the whole term by is
1.
0. 0. So we're always increasing it by 0 or more. So it's monotonically increasing. Huh?
What? Observe.
Sure. It's hard to observe that marker.
Huh? Weird. Observe.
That negative 1 to the n over 1
So I wrote.
or over n, sorry. I was just re-saying that thing.
Yeah. That.
That
Oh.
term
Okay.
is always greater than or equal to negative 1.
I wrote, just by observing, we know it's not monotone. Because Bn is greater than Bn plus 1.
But
How do you know that?
Like, just observing.
How do you know Einstein's general theory of relativity? You just observe. Just pay real close attention to the universe, you'll figure it out. Okay. Greater than or equal to negative 1. Negative 1 is the smallest it can be. Right?
Mhm.
And n always increments by 1. So, this whole term has to increment by at least 0.
Alright.
Right? Does that make sense?
Yeah.
Let's not write it all out if everyone understands it.
Can
There's
only
no
get
point in
bigger,
that.
right?
Or 0. 0 or more. Now obviously it gets bigger because this is only negative 1 once and it keeps getting bigger. But that doesn't matter.
Doesn't, well, it keeps, the second term keeps getting smaller.
Right, this
goes to zero.
Yeah, that's what I meant.
So it's gonna look like n in the long run.
Correct. Alright, B. What does B look like? So you're saying that's monotone decreasing.
Yeah.
Alright, how do you know that?
Because the biggest this could be is 1,
Uh-huh.
and the biggest this could be is 1/3. Well, yeah, it's 1/3.
And 6.
Or 1/6, yeah. And then from there on out. So,
Why 1/6?
2.
Oh. Because 1's gonna be negative.
1/9.
Oh.
Is that what you're saying?
Yeah.
So you're saying 1 comes out to negative 1/3,
Yeah.
2 comes out to 1/9, so you're saying the biggest this can ever be is 1/9,
Mm-hmm.
and the biggest this can ever be is 1.
So the biggest this sequence could ever be is 1/9,
Okay.
and then from there on out it decreases. It'll always be smaller.
But
How do I know that?
decrease. What does it mean decreasing?
He means monotonically decreasing.
Yeah.
What does monotonically mean? How do you know that that other term doesn't make it go up and down?
So you're saying the biggest this thing could be is 1, you're saying the biggest this thing could be is 1/9,
Mm-hmm.
so you're telling me that there's an upper bound of
1/9.
1 plus 1/9, so 10/9. But just because it's bounded doesn't mean it's monotone. How do I know this thing isn't bouncing up and all over the place and it just doesn't go above 1/9?
Does it bounce? It does bounce. Because of this right here.
Then it's not monotone if you're saying it's bouncing.
Hold on. You have.
It's
first
not
term
bouncing,
is
James.
10/9.
No, it's.
My next term is 3, which is negative. Oh, it's not bouncing because of this, right?
That's just too big.
This is too big that when you add the negative, then it's.
Wait, one
So
second.
3 is 1/9 plus
I didn't do
or minus
Minus whatever comes up.
1/27.
Okay, so that's you describe.
Okay.
Your,
Okay.
Your first term will always be larger than the second, so.
Always?
Trying to think of time.
I don't know how to do it.
Well, if you're that lost, then do it the way that you're used to doing it and just see what happens. So the next term minus the previous term, right? So 1/n plus 1 squared plus negative 1 to the n plus 1 all over 3 to the n plus 1. So we want to do this minus.
This is what I did in my homework.
Minus, let's see, 1/n plus negative 1 to the n over 3 to the n. And you want,
squared? Your
Sorry,
first
what?
term and your second part should be 1/n squared.
squared. So you're saying that this is decreasing, right? So you're
that's
saying
what it means.
this term is what?
Bigger.
Bigger?
Or no, it's going to be smaller.
Smaller. Smaller minus bigger produces
Positive.
Negative.
Negative, it's decreasing.
2 minus 3 is, okay. So your argument is that this is always negative,
Uh-huh.
okay?
No.
The
Yes.
whole thing is what Donnie was pointing out.
Oh, sorry. This minus this is
No,
negative.
yes.
Now, what to keep track of which one we want to be positive and which one we want to be negative, let's think about which of those is the worst case. When n is even or odd is the harder case. You see what I'm saying? We want this to be a smaller term and this to be a bigger term when we're doing this, right? So we're saying this, oh sorry, other way. We want to make this one as small as we can and this one as big as we can. And still, the difference is negative. So let's pretend that n is an odd number and n plus 1, n plus 1 is an odd number. We want to make this term right here negative, and we want to make this term right here positive. That way we show even when this is as big as it can be and this is as small as it can be, the difference is still negative.
In its fluctuations.
Does that make sense?
Yeah.
So rather than that, let's just make that a minus, and let's just make that a plus, and we're handling as the worst case. So if it's true for this case, it's definitely true for all cases. If this comes out negative.
No, that's true for all cases.
This is as bad as it can be. This is the hardest case.
For our case.
Obviously, if this were negative and this were positive, that's easier to handle. Right?
How do you know it's the worst case?
There's only two cases. This one was positive and this one was negative, or this one was negative and this one was positive.
Because it's n plus 1 changes, and that's.
And I don't want to handle both those cases. I want to just pick the harder of the two cases and show it works for that case. Look, we're trying to show that b minus a equals a negative, right?
Mhm.
And we want to show that is true. Maybe all this negative thinking is throwing you off. Let's do it the other way. Let's do this minus this, and maybe that will help your thinking.
Make sure it's positive.
So we want to show that this is positive. So we want to show that this is positive, right?
When you say it's the harder of two cases,
So what's harder to prove? When this is positive and this is negative, that this minus this is positive, or when this is negative and this is positive.
That's negative, that's positive.
See, is it harder when that's a plus and that's a minus, or when that's a minus and that's a plus?
Minus and minus.
So that's
Right. This is a worst case. Obviously, if it's true for this case, then it's true where we make that a plus and that a minus. If we make this number smaller and this number bigger, yeah, that's definitely true. Right?
Okay.
Losing anyone in that thinking? So now we just need to show that this is positive. Right? Okay. So let's go from there, showing that that's positive.
Wait,
And maybe rewrite this one more way.
What I show it's positive.
To help
by-
start
no,
make
show that
sense.
as positive. Take n plus 1.
Well, let's rewrite this one more
Minus
way. N cubed.
And that should equal out.
Oh, that's an n squared.
Positive.
Sorry.
what we're doing here is
Let's look at this.
n minus n plus 1 is positive to show that the function is decreasing. Or
Right.
the sequence is
isn't
decreasing.
that,
So we're saying the term that follows is smaller than the term before it, means that we're monotonically decreasing.
it's not n minus 1, it's n plus 1.
Oh, thank you. Yes.
Okay.
Oh, that's not gonna work as nicely as I hoped.
Well, I'm confused about it.
So you're gonna have to get
That
down
term's positive, that term might not be.
Why were we able to drop that?
this term's negative.
That term's not.
James, why were we able to drop
So
that?
you have to show that that term's more positive than that term
Yeah.
is negative.
So you're gonna have to get comment on here, right here.
I see where we did, but
I
how
know,
were we
but
able-
I'm saying, Donnie, we need to have this right
Have what?
here. -1 to
No, we just went over
Why
this.
did we do this?
Look. Ultimately, this is plus or minus 1. Ultimately, this is minus or plus 1. If this one's a positive, this one's a negative. If this one's a negative, this one's a positive.
Oh, because it doesn't matter for whatever end you have in.
Oh,
It's either going to be even or odd.
How
one
do
of the
you
two.
think about those things, huh?
Well, you could have handled both
How
cases
does your brain work?
and gone through and done both cases.
If n is even, if n is odd.
Yeah,
Yeah.
and you would have gotten these two cases. And I'm saying this case, it was obvious, the case I just erased is obviously true if this case is true.
Right, because smaller minus
Because you made
something
this number
bigger.
bigger and you made this number smaller.
Right.
So if this minus this is already a positive number, then when I make this bigger and this smaller, it's obviously still a positive number.
think of that?
I don't know how to explain how you think. So,
When you're
you're gonna need to get a common denominator here. I don't know a way around it.
How do you do that? N squared times 3n is what? 3n.
It's gonna be
Three N.
three
Are you saying how
over,
do you get a common denominator here?
it's gonna
I'm
be
saying,
three
when you
N.
do the timesing those together, what does it look like?
So that is going, so if you want to combine these two terms first, you're gonna get n squared minus 3 to the n over n squared times 3 to the n minus,
Did you do that right? I feel like you did it backwards, 3 to the end.
oh, sorry, yeah, my.
Yeah. Okay, I see, I see it.
Backwards.
I see it.
Okay, and then finish.
And then you have,
Wait, how did that happen? You have to.
Just getting common denominators.
Oh, you did that right there.
Yeah, just each term separately, and then we'll have to do it for all of them. You're gonna want to write so the camera can see it. If you guys are gonna come back and look at this, you need to try and make it look bold.
where did I put that red marker?
And then. Minus 3n plus
That's what
1.
happens with all your markers, Donnie.
They end up in my room. I found like 3 markers in my room.
You're still in the markers?
I guess so. I don't know why.
Neither do I. I wonder why we keep running out so fast. I feel like I go get a marker every week.
Well,
That's good, that was pretty.
Mr. J.
Yeah.
Mr. J puts them in the drawer.
He probably throws away too.
For class. Why are they lasting so short?
Maybe one. Last week he threw away one and he missed the garbage can outright.
Can I do
Did
this?
you get a candy bar out of it?
You get a common
Now someone
denominator.
else in the can.
That's what you're doing.
You should say, Mr. J, if you make it, give me a candy bar, if you miss, you owe me one.
That's what someone did with him.
And then cover the,
He nailed it. Okay, from here, what do you do?
you're trying to show that everything, the whole thing is positive.
What are you doing?
Oh,
No. Oh, were you distributing?
Yeah.
Don't distribute, just leave
Square
it.
terms.
n plus 1 squared, 3 to the n plus 1 times that, right? There you go.
You can't distribute into, where you're distributing the squared.
Right? Okay, now you still need to get a common denominator. Wow, it's not that hard. 3 to the n, well, maybe I'll write it all out so that you see everything happening in one go. So what do we have in the numerator here? We have 3 to the n minus n squared. This is going to be times this denominator. N plus 1 squared times 3 to the n plus 1. There's that term. Then we're going to have minus this times that, right? So we'll write the numerator, 3 to the n plus 1 plus n plus 1, right? Times n squared times 3 to the n. Over a denominator. We don't care about the denominator anymore. Why don't we care about the denominator anymore?
Because you're just looking to see if this comes out negative.
Right, we just care, is this thing positive or negative? Denominators are irrelevant. The denominator is always a positive number. You see that?
Yep.
So this is over, who cares? X, doesn't matter. So from there on out, all we care about is, does this thing come out positive or negative, right?
Yeah.
Maybe go to a new line here, and let's write out what we get. So, we're going to have to multiply that out, aren't we? get like terms.
The n plus one, just do it on the side real quick.
Yeah. So I'm gonna rewrite this term up here so you guys can see what I'm gonna do. This is gonna come out to n squared plus, well, I'll multiply by this at the same time. So we're gonna have an n squared times 3 to the n plus 1 plus 2n times 3 to the n plus 1 plus 3n plus 1. That's rewriting this term. Okay with that?
Yep.
And the other terms are already expanded out for us. So now, I need to multiply this into all those, and then minus what I get when I plug this into all those. Right?
Okay.
So we have, the first term is going to be, I can just do it like that. N squared, 3 to the what?
3 to the plus 1.
When I take this 3 to the n and I multiply by that,
It's 3 to the 2n plus 1.
3 to 2n plus 1, perfect. 2n plus 1. So that's the first term. Plus 2n, 3 to the 2n plus 1. Right? Plus 3 to the 2n plus 1. That's distributing through the 3n. Now I need to distribute through the minus n squared, right? So we have minus n to the 4, 3 to the n plus 1, minus 2n cubed, 3 to the n plus 1, minus
2n.
2n 3.
Ooh, maybe I should have factored. Oh, that was dumb of me.
What?
Yeah, let's clean this up
3n
first.
plus 1.
My bad. I have a 3 to the n here, and I have a 3 to the n here. Let's rewrite this one more way.
Yep, 2 3 to the n.
So let me rewrite this whole thing expanded out right below it.
I got 3 to the n out of everything.
I'll just write it over here, but let's write this. Let's not make this so hard on us.
3 to the n.
So I have 3 to the n. I'm factoring out of this, which is going to leave here just a
3 to the n.
3.
You can
I
factor out
a 3 to the n.
everything together.
Oh yeah, just a 3.
So then I have
1 minus
3 to the n minus n squared times n plus, well, let's multiply this one out. N squared plus 2n plus 4.
N squared.
Oh, no, that's wrong.
You can't factor out 3 to the n
Let's
unless
leave
you
it how we have it.
apply it to what's being multiplied by.
N plus 1 squared times
Oh,
3.
it's all being multiplied.
That's what I get, right? When I rewrite this term?
Yeah.
Minus, pull a 3 to the n out of that thing.
Where are you pulling these 3 to the n out?
I'll show you where each of them come from. Okay. When I take 3 to the n out of this term, I leave behind just a 3. Right?
3 to
Yeah.
the 5 divided by 3 to the 4 is
What is 3 to, maybe try this. What is 3 to the x times 3?
3 to the
3 to the x plus 1.
Oh.
Right? What is 3 cubed?
3 to the 1 to the 1 to the 1. Okay.
Right? Or I could have rewritten it this way.
Yeah.
Right? Okay. So, take 3 to the n out of there, that leaves a 3. 3 to the n, 3. Right?
Okay.
And then I just took this 3 to the n and wrote it in the front so you can see it.
Mine is different than yours. Over here we have n, like to get common denominators, wouldn't this have to be squared? Making that squared, which you have. Oh,
Yep.
Sorry, that squared right there. So making this squared essentially. That whole term squared.
Squared, good catch. Squared. Squared. Good?
Can you take, oh.
All of this,
No, I'm talking about right there. No, over one, yeah. You only took it out of that one, right?
It's timesy.
this is all times this.
Yeah.
Look, relabel this A, relabel this B, relabel this C. I have A times B times C. I can factor out a C. Right? Okay, no more mistakes? Right? Okay. So now this 3 to the n has no effect. Right?
That kind of minus itself, or what?
Because if this minus this is positive, then it's going to be without that term.
Yeah, you're right. A factor, obviously.
Yeah, you can get rid of factors, and it doesn't change anything. I should have write equals, it gives us, now we're just interested in that,
You
right?
could pull out another 3 to the end.
And this just gives us, now we're interested in that.
So you could do that twice. 3 to the end each time.
No, I can't.
Why?
So this gives me this,
3 to the n minus n.
3 to the n minus n squared, n plus 1 squared,
Oh, let's see.
times 3, minus 3 to the n plus 1, plus n plus 1 squared, times n squared. Right, did I make a mistake?
That's what I have.
Okay, so we got rid of the 3 to the n. And I don't see anything else that obviously factors. Unfortunately. So now we just gotta look at that big mess and see what comes out. So what comes out of that? Now I want to rewrite this with everything expanded underneath.
Yeah.
So
3 times 3 into n.
where do I want to put this 3? I'm gonna put this 3 over with this, making this a 3 to the n plus 1. See what I'm doing?
That's actually so smart.
So get rid of that 3 because
But then you have 3n squared, right?
Yeah.
As well.
3 times that. I just grouped it with
No,
this.
that's a
No.
minus sign.
Mark check.
Oh, that's a minus sign?
Yeah.
Oh, I thought that was a times. Okay, then don't do that.
Oh, okay. That was really cool though.
You don't need to expand your n plus 1 squared, I don't think.
I think I do.
Because you're going to be subtracting that n plus 1 squared.
But it's gonna have different coefficients.
It'll have n squared, for one of them at least.
Well, we can keep it grouped together for now and see what happens.
I don't even know where to go from now.
Keep going.
Besides-
Just keep finding it.
Never
Besides-
stops.
So multiplying this out, we get 3 to the n plus 1. When I do this 3 with that times this, n plus 1 squared, minus 3n squared, n plus 1 squared.
Wait, I'm confused what you're saying.
Okay.
He distributed the 3 times n.
I put the 3 with this and multiplied it by that.
And multiply.
3 times 3 to the n. I'm doing this multiplication, this times this. I have 3n times that times 3, and negative n times that times 3.
Oh, that negative is not, that minus 3n is not doing our other side, I see. I thought.
No, we haven't done the other side yet. I'm not done.
Another minus sign.
That's just taking care of this. Now I need to take care of these terms. Over here we have minus 3 to the n plus 1 n squared. And then we have minus n squared n plus 1 squared. Did I get all that right?
Plus. Oh no, never mind.
Still minus.
Why don't
Right.
I have n plus 1 squared in the third term? Oh.
It should have been in all terms.
It's
Both these terms get it from here.
but that
And
is
then
separated.
this term only got it from here. This term never gets it. So it makes sense that there's one that doesn't have it. So now,
What does what?
let's see what we've got here.
N plus 1 squared is always greater than n.
We're saying that this is always positive?
Yeah, it looks super
Decreasing.
negative.
Yeah, now I'm thinking we screwed up the sign somewhere. That was a negative, this was a negative, right? So positive, negative,
Negative, negative.
negative, negative. Positive, negative, negative, negative. Alright, that's right.
Maybe it's not uncommonly decreasing.
Think, how do you show how, like?
Yeah, we have one straight in here. Because eventually this is going to be massive compared to. No, it's not. Maybe we don't have a mistake. So let's multiply this one out and see what. No, that's ugly. Shoot.
What did you do in your book?
I just graphed it and then said it was monotonically decreasing. That's all I did.
But this should work.
Yeah, this should work. It's getting out of hand. I'm pretty sure we have a mistake somewhere. I'll try this again algebraically, and then when I have it all nice, I'll
So
give you guys my solution.
N squared,
I worked so hard on that.
You can keep working with it. If you multiply it all out, it might. If you don't make a mistake and you keep multiplying it all out, it should eventually work. And we could have been on the right track, and it could just be the problem requires a lot of work. I don't know how the odds are intended us to do it, though.
What if you were supposed to have,
Well, look how easy our last one was.
Yeah, that one was a lot easier.
what if you were supposed to have positive minus or positive instead of positive negative negative?
No, our assumption there, I think, is fine. Anyways, let's keep moving forward. All right, problem number 3. You ready, Janetta?
No, because that's the one I got stuck on.
You got stuck on 3?
Yeah.
No, 10 left is really low.
You are still trying.
What is it?
It's,
Given that.
yeah.
Suppose.
Oh, I lost it. Given that
And it's one.
a(n) is monotone.
Prove that and converges if and only if. What does it mean, a squared then?
a(n) like that?
Yeah.
Square-
No.
Oh, no, that converges. If
A squared 7. What does that mean?
N squared.
give me an example of a(n).
And
N. So if n converges, then n squared converges. And if n squared converges, then n converges. Now, obviously this doesn't. What's one that does? 1 over n converges. We're saying, if this converges, then this converges, and if this converges, then this converges.
so it's if and only if.
I can do this.
If and only if. So, let's do it the easy way first. Prove that if an converges, an squared converges.
Assume and squared converges.
Right? Then, the limit of an times an is equal to the limit of an times the limit of an is equal to a squared. Oh! Arm's tired. That was a big proof. One direction. Now let's do it the other direction. This way's more interesting. So now assume that the limit of an squared is equal to b. Good?
Mm-hmm. So I have to prove that it's monotonic.
We're going to use that. Given that AN's monotone, prove this converges if and only if this converges. So I'm going to use the fact that AN's monotone.
Okay.
Notice I didn't have to do that up here. Now I'm going to have to use the fact that it's monotone down here. But if the limit of this scene equals some number, and, well,
Wasn't it if you prove that a sequence is monotonic and it is bounded, then it converges? So don't.
so now we need to show that this thing's bounded.
Right.
So then there exists C such that AN squared is less than or equal to C. Now let's make sense out of that real quick. We know that AN is monotone, right?
Mm-hmm.
So it's either monotonically increasing or it's monotonically decreasing. But if it converges,
It's bounded.
then it's bounded. Well, we don't need to say all that yet. Let's keep it simple so far. We know that AN squared converges, therefore it's bounded. Is that right?
How do we know that? And well, we're assuming that.
If a monotonic,
The thing is, if it's monotonic and it's bounded, we know it converges.
right, we're proving it's bounded from the fact that we know that AN is monotone. Do you know that AN squared is monotone? No. We know that AN is monotone.
But can you, is that given from that info?
But did we prove earlier that a monotone
I think we did.
increasing times a monotone increasing is a monotone increasing?
It's a question.
No.
The question was, is it monotonic?
If they're monotone the same way,
I don't think we agree.
then the product is monotone. We didn't put a justification there. The limit AN squared exists where AN is monotone. Then AN squared is bounded, is what I have there. Then AN squared is bounded. How did I know that AN squared was bounded?
I'm not bounded bounded.
If it's
Because A is bounded, right? Because it's converging to A squared.
Finally.
The limit is
Okay.
you could only say that.
Oh, the limit is B.
How did I know that this thing is bounded? Is that even true?
If it converges. I mean, that.
Yes,
makes sense.
it's true.
Yeah, it makes sense when you think about it. But why?
Didn't you say
I
if
feel
it
like we've done
converges
it
then it's
for
bounded?
along these lines.
No. It being convergent doesn't mean it's bounded.
What's the monotonically or monotonicity assumption?
I guess we could break that argument up into two pieces and handle each case, or three pieces.
If it's constant, it's easy.
If it's constant, then yeah, we handle that case. If AN is monotonically increasing,
And not constant.
then it's bounded from above.
Below.
No, it's bounded from below. If it's monotonically
Bounded
increasing,
from
right?
Oh,
above.
and
No.
if the limit exists.
If it's monotonically increasing,
And
then
doesn't
it's
go to infinity.
then it's bounded from above. If it's monotonically increasing, it converges. I don't know that. Because AN is monotone, AN squared is bounded.
Well, didn't you?
Wait.
Well, you proved that.
So the fact that the limit of this thing exists
Makes that thing.
means that it doesn't go off, this doesn't go off to infinity. So I know
We're
that.
assuming that.
No, right. So if this thing,
Has a limit.
this is always positive and it has a limit,
Then it's bounded.
but how would I argue that it wasn't coming down from infinity
And plus one.
to what it converged to? How did I get to this thing?
You made a wrong assumption.
Oh, cause then the first,
Then a m squared is bounded.
then the first element of the sequence is bound. If it's coming down.
So let's just think about each of the cases. So if an is monotone increasing, which means it looks monotone increasing where its square is bounded though. That's a harder one to just picture and reason about. Or where its square has a limit.
We're assuming that this sequence has a limit,
Yeah.
and so we know that this sequence is bounded at least on one side.
Let's continue for a second and then come back to think about that. Because I must have had something, I just don't know what I was thinking. Should have put it on there. Anyways, if that's true, then that gives us that the absolute value of a(n) is less than or equal to the square root of c. Oh, which gives that a(n) is monotone and bounded. Which then finishes it. How did I get that bounded?
So we don't know if a squared is,
Isn't the question, how did we get that? It's monotone.
No. I know a(n) is monotone. I don't know that a(n) squared is monotone.
That's what I'm saying.
Didn't you say that if it converges, then it's bounded?
Oh, we don't need to know that.
If a sequence is convergent, then it's bounded.
at least on one side.
Is that true?
Yes.
Yeah, you said that.
Every convergent sequence is bounded.
I thought that was literally one of our proofs.
Yeah.
Every convergent sequence is bounded.
A
might be
monotone.
right.
Should I Google it?
monotone
You
sequence
said- I'm pretty sure
converges
last week
if
you
and
said
only if
every-
it is bounded.
Say that again.
A monotone sequence converges if and only if it is bounded.
Yeah. That's how we prove
But
it.
then is
That's
a(n) squared
monotone. We're
monotone?
talking about something that's
If a
not monotone.
sequence converges,
What number are you
is
looking
it
at?
bounded?
I'm looking at theorem 2.3.
Monotone converges here. A monotone sequence converges if and only if it is bounded.
Every convergent sequence is a
We have
bounded
already
sequence.
proven a convergent sequence is bounded. Okay, third sequence is bounded.
2.4.
If it converges, then it's bounded.
By the thing
That
it
makes
converges
sense,
to,
because
right?
either the first element
Oh.
is a bound.
Oh my gosh. That's what happens when I keep thinking about the real numbers instead of the naturals.
Said
Duh.
that way.
Duh. Alright. Dumb moment. Alright. So nice and simple. Since the limit of that exists, that's a sequence, converges, therefore it's bounded. So there has to be some c such that it's less than or equal to c, its absolute value, right? That's the definition of being bounded. And then, obviously, square root. That's true. Therefore, a(n) is bounded. That was a real easy proof.
I already just got to remember.
Stuck on. One stupid part.
Number 4.
Number 4. If the limit of a(n) equals a, where the absolute value of a is less than 1, then the limit of a(n) to the n equals 0. Didn't we do this one in class? If the limit of a(n) equals a, where the absolute value of a is less than 1, then the limit 0.
I get what it's trying to
Right, does this make sense?
say. Since it converges to something less than 1.
So since A converges, then there exists some index such that an minus A is less than, I did 1 minus the absolute value of A over 2 for all n greater than or equal to n. Alright, let's see my thinking here. So, Okay, that's the theorem that we're going to use. Ultimately, I'm trying to get that, let's see which part of it. So the theorem that we had before, that we proved, that's why this looks so familiar. We said that the limit of c to the n equals 0 if the absolute value of c is less than 1. That's what we proved. Is this ringing any bells?
No, it did not.
If c is a number smaller than 1, and I keep raising it to bigger and bigger and bigger powers,
Multiplying it by itself.
multiplying it by itself, look, let's look at the number line. Here's 0. Here's 1, here's negative 1. Let's look at 2 for a second. If I take 2 and I keep multiplying 2 by itself, what happens?
Yes.
It gets massive. If I take negative 2 and I keep multiplying it by itself, what does it do?
Goes really, really big.
It gets massive or really small, right? We get positive 4, negative 8, positive 16. It keeps alternating, but its absolute value keeps getting bigger and bigger and bigger.
Okay?
So the absolute value of negative 2 to the n keeps getting bigger and bigger, and the absolute value of 2 keeps getting bigger and bigger and bigger.
Okay?
Right? What about the absolute value of 1 or the absolute value of negative 1? What happens when I keep multiplying that by itself or that by itself?
Stays.
Just stays. Okay, what about 1/2?
Oh,
Numbers
because
are
it's
so
really
big.
small.
It gets way small, same with negative 1/2, right?
Yep.
So, if c is a number, this is absolute value. If c is a number and its absolute value is less than 1, in other words, it's in this interval,
Then its limit is 0.
then when we keep multiplying that thing by itself over and over again, it gets closer and closer to 0. That's what we
The
proved.
limit of Cn.
The problem
equals
is-
0 if the absolute value.
The limit of c to the n. We keep multiplying c by itself.
Yeah.
Does that make sense?
The problem we're dealing with here is the solution of our limit is less than 1.
Well, right. So here's what we need to work with. We basically need to demonstrate that a to the n is less than 1.
Right. How do you do that?
If the limit where
Or the limit of a to the n is less than 1. So ultimately a line that we need to get somewhere in our proof.
Well, we know that the limit is.
Yeah, we know the limit.
Oh, sorry, not the limit. I need a to the n is less than something is
At
less than 1.
some index, it's always less than 1.
Yeah, so I need somewhere along the lines, I'll write this right over here. Basically, the crux of the proof is getting to something like this. A to the n is less than something is less than 1 for all n greater than or equal to n. So from some index onwards, that's always true.
will you explain line 1 to me?
Since a n converges to a, then for any positive number you picked, I happen to choose this one, there exists an index such that the distance between those 2 points is less than that positive number from that index onwards. It's just a definition of convergence,
Okay.
right?
I'm seeing it now.
And this is the positive number I picked, that's
That could
like,
be 0. That could be 0.
what the heck, that's arbitrary.
Yeah.
Why'd you pick that thing? Right?
Yes.
And notice what that number is. What is that number? That's the number between 1 and A. A is less than 1.
Oh. Yep.
So I picked the midpoint of A and its absolute value, or of 1 and the absolute value of A. That's what that is.
Shouldn't
So
that be
why do you
0?
want the midpoint?
No,
Would it
because
what
then
be
it'd be
zero?
negative, an absolute value can never be less than 0.
Couldn't A be 1? Oh, A cannot be 1.
It's less than 1.
Okay.
Oh, sorry, this isn't the midpoint. This is half the distance between them. Sorry. So, let's look on the number line for a second to make sense of my intuition here. So here's 0. We have 1's over here, and the absolute value of A somewhere in between. Right?
And you're saying,
And I'm saying that AN has to be within half this distance. So take this distance, half it, AN has to be within that distance.
why do you need to know that?
Because I'm trying to get that from some index onwards, AN is always less than something that's less than 1, and that something is going to be this number.
Yeah.
Okay.
Remember what I have to work with. Let's get this picture in mind to help motivate us a little bit. Here's 0. Let's pretend A is positive so I don't have to keep writing absolute values. Here's 1. A is somewhere right here. I'm trying to say that from some index onwards, AN is always less than 1. Right? How can I do that? Well, I just keep it really close to A. Since it converges, I can just look at the ANs that are as close to A as I want. Right?
Okay.
So I'm picking a distance that I know doesn't go past 1,
Okay.
which is just half the distance between them. So don't use the distance between them, just take half of it. There we go. So now this number right here, I know that all the ANs in this interval, wherever they are always going to be less than that number, which is less than 1.
Okay.
So I know that they're within this distance, and that's going to lead to me finding this number, which they're always going to be less than, which is less than 1.
So this is just some random point. Or what I'm saying is just some random.
I could have used a lot of things here.
Right.
I just chose something I knew worked for sure. Does that make sense?
Yeah.
Alright, so there's the motivation. Okay, so let's continue with the proof. And this is going to be mostly an algebraic proof. Do you see how this is a positive number?
Yeah.
How's that number positive?
Because AN can never be greater than 1.
Because the absolute value of A is less than 1. So 1 minus something smaller than 1
It's just
over 2
positive.
is positive. Okay, so that's a positive number. That's all we cared about for that, right? Okay, so then let's write out what happens. If I know this, then what do I know? I know that negative 1 plus absolute value of A over 2 is less than AN minus A is less than 1 minus the absolute value of A over 2. Remember what I'm trying to get? I'm trying to get AN is less than something which I know is less than 1. Right?
So you need to get.
So there's my AN. I need AN less than something. What do I need
Plus
obviously
A
to
to
do?
both sides. Plus A to both sides.
Plus A to both sides. So this gives us negative 1 plus absolute value of A. Should I give it all over one denominator? I don't care how I do it. Whatever helps you guys most. Good?
Yeah.
And then, pretty sure I need to handle the cases where. Now I need to handle two cases. Absolute value of A. A can be either positive or negative, right? So, let's handle if A is greater than or equal to 0 first.
So now we're not worrying about the left-hand side of AN, right?
You're going to use the left-hand side for the negative and the right-hand side for the positive on A. I'm guessing. That's usually what happens.
Okay.
So, if A is greater than or equal to 0, then the absolute value of A is just A. So rewriting the right-hand side of that, we get AN is less than 1 plus A
Right, over 2.
over 2. Right?
Now where I'm thinking in my
Is
head.
there thinking? Keep up with me, guys. The reason we're going over this homework is to get caught up. You
A
good?
is positive and the absolute
No
value of
questions?
A is A.
All right. Once again, that's 1. That's something less than 1. So this,
Is less than 1.
right?
Right,
Good with that?
yeah.
Rewrite this one more way. That's still true, right?
Yeah.
Mhm.
Wait,
How did you take that
Why is that
value?
Okay.
oh,
Because it's positive.
Oh, okay.
Absolute value can only ever make that bigger.
okay, yeah.
So I know my ANs are always positive because they're within some distance of A. There's no way that they can get to the negatives if A is positive. So AN and A first off have the same sign. Maybe I should have started by explaining that. But then either way, AN and absolute value of AN are the same thing, and A and absolute value of A are the same thing. So my suspicion so far is the thing I'm going to put here is 1 plus absolute value of A over 2. That's my suspicion on what I'm going to put there.
We have to handle negative, man.
I don't see why you need the middleman.
Which middleman?
You just proved right there that if A is greater than or equal to 0, then AN is less than 1.
Yeah, that's true.
Yeah, we still
We just need to get to something less than 1.
Right. We did need the middleman to
Yeah,
find that out.
true. Wait, then don't you have to do less than or equal right there?
No, because A
Where?
can never be
Is it
1.
1 in that case?
No, A is less than 1. Absolute value of A
Is
is
1 plus absolute value of A over 2 equal to 1 in that case?
No.
Oh, it's always less than
Okay, so now let's handle the negative case. If A is less than 0, now I'm going to use the left-hand side of this inequality. Then we have negative 1 minus A plus 2A over 2 is less than AN, right?
Mm-hmm.
When A is
No,
negative.
minus 2A.
Where are you getting minus 2A?
A is negative, minus 2A. Oh, if A in the absolute value.
A is a negative number. 2A is a negative number. If I did minus 2A, I just created a positive number when I should have a negative number. A is negative. Look, looking up here, A is either positive or negative,
Yeah.
right? Just because A is negative doesn't mean I can go and put a negative number there.
But why would you put it in front of the
What's the absolute value of A if A is a negative number?
A?
Negative A. What's the
How do we
absolute
keep
value
track of
of
this
negative?
conversation?
It's because I literally don't understand
The
it.
absolute value of X is equal to X if X is greater than or equal to 0. Negative X if X is less than 0. What is the absolute value of negative 2?
Negative, negative 2.
Negative negative 2.
Negative A.
So if A is negative 2, then its absolute value is negative A. Does that make sense? We keep going back to this conversation, so let's just make it make perfect sense here and now.
Yeah, that makes sense.
It does make sense?
We're keeping the fact that A is negative in A. We're never pulling that out.
So if A is a negative number, what's its absolute value? Negative A. Negative 2 is a negative number. What's its absolute value? Negative negative 2. That's its absolute value.
Duh.
which so happens to be 2, but that's not what this says to do. This says if it's a positive number, leave it alone. If it, well, positive or 0. If it's a negative number, multiply by -1. There's another way you can think about it.
Okay, I actually think that. Okay.
Okay? So, if A is a negative number, then to take its absolute value, multiply by -1. Okay. Good? We good up to this line?
Yeah.
Okay. Now, what does that give us?
-1 minus
That gives us -1 plus A
A.
over 2 is less than AN. Now here comes the trick. Da, 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 da. We have negative AN is less than 1 minus A over 2.
Yeah.
Multiply both sides by -1 is one way to think about that. Or subtract AN from both sides and then add this to both sides.
Okay.
And subtract this from both sides, I mean. There's another way to think about it. Does going from here to here make sense?
Mm-hmm.
No?
I'll never do that.
Multiply both sides by -1 and flip the inequality. Right? What's AN times -1?
Negative AN,
Negative AN. What's -1 times -1?
net positive,
What's A times -1?
negative. Okay.
And then we just flip the inequality.
Value of A.
Or swap sides on
Yeah.
things. Same way of thinking about it.
Oh,
We good with the algebra there? Okay. Da-da-da-da.
Oh my goodness.
Perfect.
Awesome.
Oh my good mathematical laws.
I don't think you have laws in math.
Wait. What? If you take the absolute value of both sides of it.
The absolute value of AN and negative AN are the same thing. Absolute value of A and negative A are the same thing. I just rewrote it a different way. I mean, maybe I should have.
I get it. I actually 100%
Everyone get it? Or should I add a step in there to help it make sense?
I don't know.
I see it.
Okay, there we go. So that's what we were trying to get. Absolute value of AN is less than 1 for all n greater than or equal to from some index onwards. Oh, we don't want less than 1 only, we needed a positive number less than 1. Now remember where we were trying to get. Where are we trying to get?
The limit of-
This thing equals 0.
If. Oh,
That's where we're trying to get, right?
okay.
And I think I can just write it out. How should I write that? Well, I'm going to use a comparison limit, but maybe I need to specify this one thing first. Since the limit of what does that equal?
0.
0. So since the limit of that thing equals 0, comma, and since the absolute value of AN minus 0 is less than Oops.
And to the end.
Yeah.
Okay, so what line 5 is saying,
Line 5 is saying an is a smaller number than a number smaller than 1.
right,
Right? So this number to the n, the limit of this sequence is 0. Right?
alright, because of the lemma.
And then comparison limit. An is smaller than this thing.
Okay.
So this to the absolute value of this thing is smaller than this thing. It doesn't matter either way. It's absolute value.
Less than 1.
So this thing is smaller than this thing. So this thing to the n is smaller than this thing to the n, right?
Mm-hmm.
And then this is just a comparison limit. We know that this converges to that, therefore this converges to whatever's there.
Why do we know that an is less than that number? Oh, right there. Okay.
I'm kind of confused on, since the limit of that equals 0. Why did you make that a sequence?
So this thing right here,
Oh, just some, it's just
For the
some,
comparison limit.
we're using this fact right now. Here's C, a number smaller than 1.
oh, okay.
So this equals, the limit of this equals 0, right?
Mm-hmm.
So now we can use a comparison limit with this thing. Right? I have bn minus b times some constant, and this is always less than, I guess we could have an equal sign here with the comparison limit.
Okay.
So if this is always less than or equal to this from some index onwards, and this converges to this, then this converges to this. That was the comparison limit.
In your an to the power of n
Uh-huh.
minus 0, where did you get your 0?
I know that's what it's going to converge to. I was just setting it up how you guys are used to seeing the comparison limit. The way you've seen comparison limit is something like an minus a less than or equal to some constant times
B.
bn minus b. If this converges to this, and this inequality is true from some index onwards, then this converges to this. So this converges to this, and this inequality is true from n onwards, therefore this converges to this. Does that make sense?
Yeah, it makes sense.
I was
but-
proving it converged to 0. That's why I was proving, so I know that a 0 is going to go there. And I already know that this converges to 0, so I know 0 goes there.
I just feel like that's a little presumptuous to just put the 0 there.
Well, I can't change what I know. I'm using the fact that I know this. I'm just rewriting what I know here, how the comparison limit is set up. I didn't need to write it out all this way, I was just trying to make it obvious to you guys. I'm using the comparison limit.
Oh.
That's why I took the time to write the minus zeros in there.
In the one, this constant. One.
And yeah, and I also put a 1 there to help you see we're using the comparison limit. So I was just making obvious, hey, we're using the comparison limit. Good?
Mm-hmm.
Alright.
Okay, this next one.
8.
I think essentially what we have to do is prove that it's monotone and we have it.
If Sn equals that where Bn is bounded and 0 is less than or equal to R is less than 1, then Sn converges. No, Bn is non-negative.
Wait, we're doing 8.
Isn't that what I was reading?
No. Oh, okay, say that again. Maybe you were right.
So 8.
Sn. Oh yeah, you were right.
Proof if Sn is equal to B1R to the 1 plus B2R squared plus B3R cubed plus dot dot dot. Does it end or does it go forever? Plus B to the n, R to the n.
Goes forever.
Oh, this is the nth term. So we're writing out a series. S is a series, right?
Yeah.
So the nth sequence, the nth term in our series looks like that. And what else do we know? Where Bn is bounded and R is in between 0 and 1. Let's see more. Try and pick out a better marker. Where Bn is bounded and 0 less than R less than 1, is that what it was? Less than or equal to R less than 1.
0 to the n.
Then Sn converges. And I wrote for some reason, no, Bn is non-negative, so I'm guessing that was in the problem. I forgot to write it. Alright?
Yeah, the end
Says
is
that?
non-negative numbers.
Okay. So Bn's non-negative, and we can use that fact. Okay, so let's see. We're trying to get that this thing converges. How are we going to show that this thing converges?
Show that's monotone and it's bounded.
Yeah, we're going to show that it's monotonically increasing and it's bounded. The fact that it's monotonically increasing is just obvious because every term is positive. Right? R is positive or 0, so we're only adding
Very
positive.
obvious it's bounded too, would you not say?
R is obvious it's bounded.
R is between right there,
Yeah?
and it's a multiple. R is a fraction.
What do we know about R? We know that R is smaller than 1. And we know that the limit of R to the n is 0. That's what we know about R.
So that multiple factor gets
So
smaller as well.
since all the terms
Are positive.
are positive or 0, then it's monotonically increasing. Right?
Yeah.
2, since Bn is bounded, then there are just m.
Wait, how do we know Bn's bounded?
It says,
It says it is.
Says it is.
Such that Bn is less than or equal to m for all n in natural numbers. Right? Three. Then S sub n is less than or equal to m times the sum from k equals 1 to n of b sub k r to the k. You okay with me using this summation notation instead of rewriting that thing out?
yeah.
Oh, get rid of the b's.
How can you carry that right?
R to k. Let me rewrite this one more way. Maybe see where the summation notation comes in. You should have written it from the beginning. I don't like not using it. You guys need to get comfortable with it. So what is S sub n? That's the sum from k equals 1 to n of b sub k r to the k. That's what S sub n is. I just rewrote out this. But I didn't use stupid notation. Right? You good with that?
Yeah.
Okay, and then that is less than or equal to, maybe write this, and then you guys will see the algebra as I go. Should be my algebra, so I'll pass this these sums.
N is the
So-
largest B sub K.
B sub n is always less than or equal to n. N is the number that's bigger than all your b's. So go and replace every single one of those b's with an n, and you could have only made it bigger. Does that make sense?
Because it's bounded by n.
B sub, the b's are. The coefficients of that, if you want to think about it that way. Okay? And now, what the heck, how did I do this?
We know that can happen. Since it's a constant.
Factored an N out of every single term.
Yeah, does that make sense?
Yeah.
Okay. That's the part I was worried about with you guys. And now, what does this equal? N times, what's r to the k?
It's r to the n.
No, it's not. You know how to evaluate
Oh,
the
k is
sum.
equal to 1 is 1. Well, it's going to be r.
Geometric
Whatever it was
series.
called.
Geometric.
You know how to do this. What is it?
You're talking about a geometric series from chapter 1.
Yeah.
You guys can do it.
Our first term minus r to the n plus 1 over 1 minus r.
Yeah, that.
Right?
I would have had to pull up.
Because that's what that equals.
Don't you remember?
What's
Ooh.
the geometric series?
That didn't start at 0. Does it have to start at 0?
Well, it is a series. Which is a sum of sequences which starts at 1.
Yeah, why do I have a 1 in my notes? I have a 1 right here, which isn't right. Right? That's a typo in my notes. That should be r.
Geometric series.
Yeah, I think it should be R.
Don't go so far back.
Let James search geometric series.
Geometric subgroup. It's 1. Oh, if k equals 0, it's 1.
Right, but I started k at 1.
So it's r.
I'm pretty sure that's right.
Should just be R.
Well, for this, that's for any net. For any number.
It's 1.
When k starts at 0?
Or for this series.
Right, that's when k starts at 0.
Uh-huh.
What about when k starts at 1?
Then it's R.
It's gonna be R to the first term,
Should we
right?
just rewrite this in terms of 0 and figure it out? How could I have rewritten this with a 0 there? Then that would make this a k plus 1. K plus 1. Up to n minus 1. To get the same thing. Right? Let's think about it that way. So if I force this to be a 0, so we still have an n, we're going from k equals 0, now we're doing r to the k plus 1.
It's a R.
And I'm pretty sure n times r minus r to the n plus 1 over 1 minus r. I guess we could just think about it for a second instead of doing it the hard way.
First 5 terms each way.
Or just add it, who cares? Okay, let's make this real easy on ourselves. This is also less than or equal to n, the sum from k equals 0 to n of r to the k, right? I just added a term. I added an m. Still true. Okay. You go with my thinking there?
You just added an n.
I added an m.
Cause the first term.
I went and started, instead of starting at k equals 1, I started at k equals 0.
Which is 1 times.
What do I get when I plug in 0 there?
You get 1.
1 times m. So I basically added an m to my
Series.
sum, yeah. So we good with that? Okay. And so let's see, what does that give us? That gives us m over 1 minus r minus m r to the n plus 1 over 1 minus r. Is that how I want to do that? Maybe rewrite this one more way. That's equal to m over 1 minus r plus negative m over 1 minus r times r to the n plus 1. Good?
Yeah.
Well, maybe you're confused by writing all this. I'm trying to write something out that it's obvious what's going to happen when I take the limit of it.
Take the limit.
I'm trying to get s of n is bounded, right? So maybe just write it here then. Then the limit of s of n, or maybe even write it this way. S of n is less than or equal to the limit of s sub n is less than or equal to the limit of m over 1 minus r plus negative m over 1 minus r times r to the n plus 1. And what's the limit of this thing?
The limit, the sum of the limits.
Yeah, the sum of the limits, and then over here you have a constant times that. And the limit of this thing is going to be...
R to the n plus 1.
Oh wow, I really lost you guys on this. Okay, let me write it and then we'll go over it again. Therefore, s of n is bounded. 6.
It's
Therefore, s of n converges. Okay, let's recap everything we did and cover the thinking as we go. Okay, so I'm trying to prove that s of n converges. How am I going to prove it converges? I'm going to show it's monotone, in this case monotonically increasing, and I'm going to show it's bounded. Every monotone bounded sequence converges. So first show it's monotone, then show it's bounded. Okay, let's show it's monotone. Well, all the terms in that are positive or 0.
Then it's what?
So the next term is always greater than or equal to the previous term. So it's monotonically increasing. Okay, so we got that. Bounded is the hard part. Well, we knew that the coefficients were bounded, the b's were bounded, right?
How did we know? Oh,
It's given to us in the problem. It's given to us that they're bounded and that they're positive,
Does that mean they're constant?
or not negative. Yeah, they're constants. They're just numbers, right? Since Bn is bounded, then there must exist some number big N such that bn is always less than or equal to big M. Doesn't matter which of those coefficients you're talking about, it's going to be less than or equal to M. Right? Okay. So now remember what we're trying to do. We're trying to show that S of n is bounded. I'm trying to find some number that S of n is always less than or equal to.
Right.
That's how I show S of n is bounded.
Right.
Well, what's S of n equal to? It's equal to that, just writing it right out, right? It's less than or equal to that, because we put in the m's,
The max.
Which is the
max
max of Bn.
right?
Right.
Factor out n.
Yeah.
Add another n,
It's definitely less than.
right? Which is equal to this. Okay. Now we already know this is monotonically increasing. So adding more terms, increasing n, gives you a bigger number, right? So I know that S of n is definitely less than or equal to its limit.
What?
It's monotonically increasing.
And converges. Maybe.
Well, this thing might not exist. We don't know that this thing exists. But if this thing exists, S of n is less than or equal to it, right?
Oh, because
Because
it's
it's the biggest
monotonically increased. Okay.
You can kind of ignore this step if you wanted and go straight to this.
Okay.
But either way, it's less than or equal to the limit of this thing. Increasing our n's only made it bigger. It didn't make it smaller.
Right.
Right?
Okay.
Now what is the limit of this thing? Well, the limit of that is just that. The limit of this, well, that's a constant, but we're times r. What's r?
1.
Less than 1.
Oh. Oh yeah.
So what's the limit of r to the n?
0 or 1. 0.
0. If r is the number between 0 and 1, what happens when I keep multiplying r by itself?
Oh, it gets closer to 0.
It gets closer and closer to 0. So the limit of this thing, we have 0 times something is 0 plus that. There, I found a number. M over 1 minus r, that's a number.
How is negative n over 1 minus r constant? Oh, it's a constant.
Not n. We're doing the limit as n goes to infinity. There's no n's.
That makes that. Okay.
Right. What does this go to as I increase n to infinity? It's the same thing.
Yeah.
It doesn't change. That's what I mean by constant.
Okay.
That make sense?
Mm-hmm.
So, S of n is always less than or equal to this thing. So it's bounded. Ta-da! Woo!
Yeah, I got right. Yeah. See if I can get myself. Sure.
Maybe I need to, like, do like a midterm test on chapter 2 and 1. Should we plan on that next week?
Yeah.
And we'll just do an in-class test.
Wait, how will that work?
You stand
You'll
up.
come in, you'll have a 3-hour test. You'll do problems that I choose from 1 and 2. You'll have all class to do it. And at the end, I'll grade it, and I'll make it a big part of your grade.
Okay.
Make it like 50 points or something like that.
Okay. We have Thanksgiving to study. What will be the problems I
I
can
did not
have
have
homework?
Thanksgiving to study.
Yes, I will only pick homework problems.
Only homework problems you've done, or
I don't know what you mean. I will only pick homework problems.
there's
She's
some-
saying
Hopefully you've done them all.
Like in at the
all
end
of the
of it.
homework problems.
Yes.
Any of
exactly.
the homework problems, not all of them. I'll go through and I'll pick some of the homework problems. And I'll probably get like 6 problems.
Are all of the homework problems the ones she has to memorize?
No, only the ones assigned. Yes, all the ones assigned.
That's good.
Alright, so let's crank through 2.4 homework real quick. Oh, that homework was real easy.
Don't erase it.
2.4?
Yeah, don't erase 2.4.
Oh, don't erase this? Sorry.
I'm good.
It's too late.
I can come over here and use this. Sorry.
How late is it?
2.
Is that an upper bound or exactly what it is?
No, it's like greater than the allowable. Like
Alright.
greater than some index.
1, I don't know what the question asked, but I have
True.
A, true, B,
Observe that.
true,
C.
C,
true.
false.
Oh. No, we
D,
proved it.
false.
No.
And for the counterexample here, a negative 1 to the end.
Seems how they were all true.
True, 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 false.
Well, okay then, I got those two wrong. Guess I'll just get docked.
Let me write down all the answers I have, then we'll pull up the questions and go through all of them. Because a bunch of these were just multiple choice items, right?
Mm-hmm.
A, true, it's bounded is what I said, not sure why. B, I said false, and I wrote 1 over n for some reason. C, false, and I wrote n for some reason. D, true. E, false, and I wrote n. Three, A, I have 1/4, 1/7, 1/10, 1/13, 1/16.
116, it's 112.
Did I make a mistake?
Wait, did I make a mistake?
I don't know what this question is answering. I'm just writing what's on my paper. It's very possible I could have made a mistake, so we could relook at it and see if I did.
B, 16, 17, 18, 19, 10.
Da-da-da.
4. Peak interceded 1.
Well, we definitely disagree here.
K, 2K.
3K4.
And then the last one's a proof that, well, Deere wants me to go over all these. You have, can someone pull up the questions?
Yeah, I am. Zoom into them.
Jeez, that is not uploading. YouTube just calling it crap that they're uploading?
Using the school's internet,
Yeah, but it's usually. Okay, it hasn't changed since 2%.
it's being used a lot right
On the upload side of things.
Yeah, usually I can upload mine here. Anyways. Alright, so let's, question 1A. Maybe I have an iPad.
Every bounded set is closed.
Every bounded set is closed.
Mm-hmm.
Or maybe a subsequence of a bounded sequence of bounded.
Oh. Sorry, I'm looking at 2.5.
Yeah, it doesn't sound like what that's answering.
2.4.
2.4.
A sub.
Number 1, each of the following statements, or for each of the following statements, determine whether it is true or false just by our answer. A subsequence of a bounded sequence is bounded. True. Obviously, right? If the sequence is bounded, the subsequence is bounded because the subsequence has the same terms as the sequence.
Total sense.
Right? Next one. A subsequence of a monotone sequence is monotone. Obviously, the whole sequence is increasing, then any subsequence we take is going to be increasing. Same with decreasing, same with constant.
What page are you on?
I don't know. Oh, 46. C. A sequence, or a subsequence of a convergent sequence is convergent. That was actually a straightforward, that's a proof that we did.
Yeah, and you
If
said
a sequence
false.
converges, then its subsequence converges. I did? Then why did I write true? And then next, a sequence converges if it has a convergent subsequence. False, -1 to the end. As a subsequence, just 1, 1, 1, 1, 1, that converges, but the sequence itself doesn't converge.
Okay, but
Okay.
we go to C again. Subsequence of convergent sequences convergent. That
It's
makes
the same thing as the two.
We proved that
before.
as one of our theorems. We proved that if a sequence converges, then all its subsequence converges to the same thing it converges to.
okay. Oh, a convergent subs or a subs.
Subsequence of a convergent sequence.
I have a sequence that converges. Take a subsequence. It also
I'm
converges, and it converges to the
Choosing a
same thing.
subset and a subsequence. Subsequence has to
subset
go on.
can't convert.
It goes to infinity.
Right.
Sequences. Sequences like every fifth element or something. Subsequences.
Okay. Da 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 da. Number 2. For each of the following statements, determine whether it's true or false. Okay. Every sequence in the interval 0, 1 has a convergent subsequence. True. Every bounded sequence has a convergent subsequence. We proved that. Every bounded sequence has a convergent subsequence. We proved that.
Mm-hmm. We've already done all of these.
B. Every sequence in the interval 0, 1 has a subsequence that converges to a point in 0, 1. False. 1 over n. That's a sequence in 0, 1. It converges to 0, which is not in the open interval 0 to 1. C. Ooh, C. Every sequence of rational numbers has a convergent subsequence. What do we write there?
False. And.
False. N. So there's an example of one that doesn't. That's in the rationals.
Okay, hold on.
Why would
Every
it not have a? Oh. okay.
Sequence of rational numbers has a convergent
Subsequence.
Can a
No subsequence of n converges.
If you have the sequence n,
That's
can you
not the
also have a
sequence.
subsequence equal
That's
to
not-
n?
Say that again.
You have the sequence n. Can a subsequence also be n?
Yeah. N is a subsequence of n. You just picked all the terms. Remember how you get a subsequence? You kind of just pick which terms you want, but you have to pick infinitely many still.
Yeah.
Okay. What were we on? D?
Yeah.
If a sequence of non-negative numbers converges,
It is
its
also-
limit also is non-negative. Yes, we proved that. We proved that if a sequence, maybe we proved the converse of that. If a sequence of non-negative numbers converges, its limit is also non-negative.
No, we didn't prove that. If it's
We
positive.
proved
then
something
it's-
a lot like it.
We didn't prove positive, but I think we proved that if it converges to
A non-negative.
a non-negative number, then from some point onwards, all its terms were non-negative. Anyways, true. And then E, every sequence of non-negative numbers has a convergent subsequence. False. N, once again.
Where did that C. Oh, not negative.
Alright, 3. Consider the sequence AN where AN equals 1 over n for every index n. Write out the first terms of each of the following subsequences. That's what
It's 16. I'm an idiot.
So, when you plug in 1 for k, you get a sub 4, which is 1 over 4. When you plug in 2 for k, you get a sub 7, which is 1 over 7. When you plug in 3, you get a sub 10, which is 1 over 10. When you plug in 4, you get a sub 13. And then, obviously, once you get your first one, they're just going to increment by 3. So, yeah, that's right.
I didn't know that.
B is going to be the same thing. You start at 5 and increment by 1. So 6, 7, 8, 9, 10. C, you're going to start at 1, 1 squared, 2 squared, 3 squared. So 1 squared, 2 squared, 3 squared, 4 squared, 5 squared. Yeah, those are right. Alright, 4. For each of the following sequences, find the peak indices, justify your conclusion.
See, I
So
don't.
here we're looking at 1 over n. And I'm saying that every index is a peak index.
1 over n.
Yeah, so the one that we're looking at here is an is equal to 1 over n.
Because it is monotonically decreasing.
Yeah, it's monotonically decreasing. Every sequence is a peak.
Every
Or every index is a peak index. Plug in 1. Everything after 1 is smaller than or equal to 1. Plug in 2.
I thought 1 would be the peak index because it's the biggest out of all
What does it mean to be a peak? It means it's bigger than or equal to everything that comes after.
So 1 is a peak index. It's not.
So is 1/2, so is 1/3, so is 1/4. Every index is a peak index. Let's look at the next one. The next one is -1 to the n.
Just even numbers.
Obviously all the evens. So 2 to k. 2, 4, 6, 8, 10, etc. -1 to the n times n. None of them, because that's going to get bigger and bigger.
Yeah.
And then D, -1 to the n over n.
That's not even bigger. I don't see it.
The n. It alternates, but getting bigger and bigger every time the absolute value. So there's no peak. And then D, let's try this one out so we can see it. This one's -1 to the n over n.
So it's going to have a peak of negative.
So this thing's getting smaller and smaller as it's zooming in. The absolute value gets smaller and smaller as it zooms in. So it starts out, let's see. When we plug in 1, we get -1. So it starts out -1. Let's try and write it like this. Say that there's 1, there's 1. So it starts out -1, then it goes up to 1/2, then it goes to -1/4, then it goes up to 1/8, right? So every positive one is going to be a peak. So once again, your k. All those make sense?
Yeah, I see. It does make sense. What was the homework for this?
Huh?
What was the homework?
I don't know.
James?
So now let's do
What problems?
the only proof.
Oh, it's
In the
1, 2,
section.
4, and 9.
9. The sequence AN was defined to be bounded provided that there is a number m such that the absolute value of AN is less than or equal to m for every index. Show that AN is bounded if and only if there are numbers A and B with A less than B such that AN is a sequence in AB. Okay.
Didn't we already put this?
It seems really familiar, doesn't it? So here's how I wrote the proof down, what we're trying to prove. Prove AN is bounded if and only if there exists a B such that AN is in AB. Understand the question?
No, not really.
So we're saying this sequence is bounded.
Okay.
If and only if I can find two numbers so that it's always in between those two numbers.
Oh, okay.
It's pretty intuitive. And if it's always between those two numbers, then it's bounded.
Isn't that like the definition of bounded?
Almost. So let's do it this way first. 1. Let an be bounded. What does that give us?
And there means there's two numbers.
Then there exists m such that the absolute value of an is less than or equal to m. Switch markers. This one's garbage. That caught me.
This should get better.
That's good. So screw that. Less than or equal to m. Right? Well, what does that give us? That gives us negative m is less than or equal to an is less than or equal to m, which gives us that an is in negative m. Alright, that way was easy.
A, B, negative n.
I think that's good enough, right? We found two numbers where that's the case. And then, next week's pretty easy too.
Pick the max magnitude. Make that your n.
Let an in AB. 4. Let m equal the max of the absolute value of A and B. 5. Then negative m is going to be less than or equal to A. It's going to be less than or equal to an is going to be less than or equal to b is going to be less than or equal to n, which gives us
That's the value of n.
negative m less than or equal to an less than or equal to m, which gives us absolute value of an less than or equal to m gives us
Okay.
an is bounded.
Will you explain the form why?
Sure will. So A ends in between A and B, right? Let's pick, give me an A, give me a B.
2 and 5.
Let's make sure that A is negative.
Negative 2 and 5.
Alright, so we've got negative 2 and we've got 5. And we know that A ends always between those. Right? So I'm saying if A ends always between negative 2 and 5, then it's always between negative 5 and 5. Right? That's what we're saying here. So what has a bigger absolute value, A or B? Make m equal to that thing. In that case, it's 5. And so if
Equal the set.
it equals the max, whatever's bigger out of the absolute value of A and the absolute value of B. Does that make sense now?
Yeah.
Okay. So, in other words, negative m is for sure smaller than A and B, or negative m is less than or equal to A and less than or equal to B, and positive m is greater than or equal to A and greater than or equal to B. That's what we know for sure for this. Now we
Not
try
really
it.
equal.
Less than or
Well, it can't really, the negative can't be equal to B and the positive can't be equal to A. And the negative of this, never mind. There's 4 cases that can come out, but it is equal in some of those cases. Anyways, so we have negative m less than or equal to A, less than an, less than or equal to B, less than or equal to n. So you're good with this, right?
Yeah.
Okay. Now get rid of the A and the B, just rewrite it with the m's. or any step that's weird. All makes sense? And that was all the homework for that.
I didn't even look at it.
Wow, 2.4 was easy. So that's the end of all this 2 homework, and then after that we're ready for 3. So next week, I'll have a test ready for chapter 1 and chapter 2. Do you want to include preliminaries on there?
No.
I may probably pick 6 problems. So the question is, where do you want those problems to come from? You don't want them to include the preliminaries?
Or
No.
preliminaries.
Proving things like how to use the distributive property with minus.
That looks very scary.
No.
Alright, we can leave the preliminaries out of it. So I'll pick 6 problems. They're all going to be proofs. I'll tell you that. Everything I pick will be a proof. I'll most likely pick this one since it was the only proof in this section. Most likely.
They'll all be proofs.
So you want
Of course.
Whoa.
Okay.
Why would I waste your time?
No, I'm kidding.
And then
I have a question on how
you're also going to come with homework 2.3 and 2.4 done. And I'll start actually grading homework now.
How do you?
So I'm just giving you guys full credit for everything up to 2.3.
2.34.
So 2.3 and 2.4,
Should we figure
I'll
out
actually
2.3
grade.
and B real quick?
You just did 2.4.
what?
You just did 2.4.
I know, and I did 2.3. So I'm actually going to grade those.
Hey,
Hey,
how do you grade proofs? If our proof has a mistake, do you kill our proof?
okay. The way I generally grade proofs, there's a total of 5 points you can get on a proof. The first point is you knew where to start. That's your first point. I don't care what you write on a paper, if it's clear to me you didn't even know where to start, you get 0 points. So your first point comes from demonstrating, hey, I at least knew where to start.
I have a direction.
Yes. And then from there on out, it becomes a question of how you messed up. So if your only mess up was something like a sign, a small arithmetic error, that's minus 1 point. So because it's weird in that I can't just say like 1 point for the right answer. You already know the right answer when you're going to prove something. It's given to you in the problem. So the right answer means nothing to me. I don't care about your answer, as in the right answer at the end of the proof. So you get minus 1 point if you made an arithmetic error of some sort or something small, some sign error.
My thoughts make sense.
2 points means you made a small logic error.
Sorry, I looked over.
But that does not imply that.
So,
Sometimes it's hard to come up with an example on the fly
and my thoughts are.
because it's like
And so I start reading it. making
I don't know how else to say it. A logic error. Your logic was bad.
And then it starts.
You thought
falling
that this
into
was
place
enough
for
to
me,
show this,
and
but
I
it
just started
wasn't.
reading it right.
Where you got confused in your head and you were.
So like that.
I don't know, my students, I see it all sorts of ways, like.
And so I'm reading it.
They accidentally,
and I'm
proved the
thinking,
problem
oh,
backwards.
that's positive. And I looked over.
That's something I minus 2 points for, as long as it was all valid, but they actually proved it's commas or something like that. That's a real extreme example of logic error, but logic errors gets minus 2.
If you have a negative where it should be
Minus
positive,
3
it will no longer work.
Is demonstrating a misunderstanding of
Yeah, at the end of your proof.
the material.
I know that. I'm saying that's why I got C's in algebra. You know, most of my tests.
So you go off and you prove something, but it's not really what we were trying to prove, and you seem to just misunderstand the material.
Look at the initial problem.
So
Gauge
you
where it
said this, you interpreted this wrong, you went off and proved something that wasn't related. I'd probably give you 2 points for that.
Well, what if I'm
So-
going through it?
Minus 1 arithmetic
Answer, and so
mistake,
there's
minus 2
positive,
simple logic mistake,
or there's a
minus
negative,
3
and I'm
mistake
thinking
in
of it
applying
as
the
negative,
concepts.
rather than positive.
Minus
It'll
4
still
is
work out
you only knew where to
right
start.
answer.
Minus 5 is you didn't know where to start.
You shouldn't mark.
And know where to start doesn't mean you write the first line of the proof. It means you were able to like unravel the definitions.
Yeah.
That's what I
But
mean by
then
you
how
know
would I
start.
know the right answer if it's an algebra proof?
So that's typically how I grade proofs.
And how long do we have?
You have until you're done.
It's an open textbook.
If
Yeah,
you're
so
doing the
how would I
math
know
correctly,
that?
but writing the wrong stuff and come to the right answer,
Cause that would,
people would see,
it should be,
oh,
in my opinion.
he wrote this, but.
You should
this
be able
is what he
to, we
meant
should be able to
instead of
let
stuff,
us see our theorems and stuff.
Cause you get the right answer.
I wanna say
Or you
open
do the math
textbook.
wrong. You act.
The only
like
thing I'm worried
negative
about-
instead of
okay.
Positive, you'll get the wrong answer.
I'll say open textbook, but then hard deadline,
On the right.
have to be done by the end of the class.
Oh, it might be right.
Well,
You
yeah.
look at the initial
No,
problem,
we
and
have to
think,
The,
oh, big number minus
if you're
a
viewed
small
that
number
way,
should
a lot of times I
still
let
be
people
pretty
like
big
finish
number.
after school.
You come to the end of your proof and you're like, oh, I have a
If
small
they weren't
number.
able to finish
I'm
the
used
class.
to
Let's
2 hour
go
tests.
back through that.
So,
See.
we'll do a hard deadline of 3 hours.
Algebra is.
We'll make an open book,
Because you can
and
have.
you'll most likely have 6 proofs.
Will you tell us what section?
I honestly have no clue how to make the test.
I go through.
So,
I'm
not even promising 6 questions. I'm guessing that that's about what I'll do.
I messed up.
Okay.
What if you just
Maybe
do a
more.
proof from each section? Okay.
Maybe that's what I'll do. Maybe I'll think that section was too easy and I won't pick anything from it. Or maybe I think, wow, do these guys even know what continuous is? Or not continuous, what a limit is, and maybe everything will be like just proving direct limits and I'll just make up problems.
That would be such a fun test.
That would be a
so
fun
hard.
section.
But most likely what I'm gonna do is pick 6 problems from your homework that I think well capture the material up till now and have it do that.
Okay, so to study for the test, just go over our homework.
If you can do any homework problem without looking at your solution,
Do like
then you'll be fine on the test.
How many sections
I
were
don't think we
one?
need this.